2, we're going to talk about polynomial functions. Okay, polynomial functions. The best group of the function that we're going to use for application in future. Okay, you know that this is a combination of powers of x that we're going to call it a polynomial function. So if a function, okay, if a function f is defined, okay, by a polynomial, like f of x is equal to, is a combination of powers of x. So start with the power, the highest power. We usually go with the first coefficient, we call it an, x to the n. Okay, 2x to the fifth, for example, that's the case. Then if we keep going down, it's going to be an minus 1, x to the n minus 1. And we continue to get to the first power, we call it ax. And that last number, or we call it a0. That's very a standard notation that we're going to use. Okay, if a function f is defined by a polynomial of this type, then f is called a polynomial, okay, a polynomial function. Okay, this is going to be 1. Of course, you know, where these numbers, where an, comma, an minus 1, just keep going up to the a1 and a0 are going to be only numbers. Okay, it's going to be numbers. You know the property of the polynomials from, you know, in algebra, but we're going to look at this from the function point of view. Okay, the function point of view. So it's a combination of powers of x. All the powers must be positive, and they must be, okay, positive integers. Okay, positive integers. So, for example, we can quickly test to see that we are familiar with. Okay, determine if, okay, if the function is a polynomial. Okay, if it's going to be a polynomial, just, you know, make sure that you remember it, and we already done some of these case. So for example, f of x, okay, f of x is going to be 5x cubed minus x squared plus 3x minus 1. This is going to be a polynomial. Okay, it's a polynomial. Start with the third power and just keep going down. Okay, it's a combination of powers of x. You see combination of powers of the x, and there is no negative sign. You know that from function point of view, we already talked about it. The domain of this function is all real numbers. So this is a polynomial. But if you be given this one, you see if you get something like a g of x is equal to the x to the fifth minus 3x squared plus 5 over x minus 12. As you can see, this is not a term, because a term means a product. Okay, a term is going to be a product, a number, and a power of x. So this is 5 divided by x. Okay, so in this case, this is not going to be a polynomial. Not a polynomial because this is not a term. A term is going to be something multiplied. Okay, a number times the powers of x. Besides, you can move it up. You have a negative exponent, and you cannot have a negative exponent in the case of a polynomial. Okay, so we reject this one. Any question? And another one is going to be, if you be given this function, okay, g of x equal to, given g of x equal to the, let's say, 3x squared plus 5 radical x plus 1. Again, this is not going to be a polynomial because this is not going to be a term. Okay, you know that radical x would be x to the half. X to the half, so it's not going to be just a term. A term is a number. Okay, a term is going to be a number times a power of the x. Okay, any question? So be ready for it when we ask you, give us the example of a polynomial. Is going to be just a combination of powers of x. Okay, start with the highest powers and again going down. So what we are going to be interested in the case of the polynomial is, you see, we would like to investigate these not as in algebra. In algebra, you know that you add, subtract, multiply, divide polynomials. But we would like to look at it as a function. As a function, the domain of this function is set of all real numbers. Okay, domain is going to be all real numbers. We want to investigate what is going to be the graph of a polynomial. Okay, so what is going to be the graph of a polynomial? So this is the question that you are going to answer here. Okay, question is going to be what is a graph, okay, of a polynomial function, of a polynomial, okay, polynomial function. What is the property of that, you know, of that graph? Now, the polynomials, the graph of the polynomials are going to be very, very nice one. And this graph would have this type of, okay, property. So we are going to define what is going to be the graph of a polynomial first. You know that the graph is going to be just a collection of points. So a graph of a polynomial would have some special property. Okay, the graph of a of a polynomial is going to be, we call it, you know, in calculus, we call it is smooth and continuous. Okay, a smooth and continuous means this graph is going to be one piece. Okay, it's going to be one piece. There is no gaps, no holes, or no sharp corner in the case of the polynomial. Okay, so this is going to be the case that we're going. So this means if y equal to the f of x is a polynomial, it's going to be a polynomial, then the graph, you see the graph has, okay, it's going to be continuous, it's one piece, is going to be continuous with, okay, with no gaps, if you like, and or, okay, no holes, if you like. It's going to be just one piece. We call it a smooth, and there's not going to be any sharp corner in this case. In calculus, we have some property to define what you mean by the smooth. But in this case, this is going to be the case. Are done? So this is going to be the graph of a polynomial. You see the example. See, this one is going to be a graph of a polynomial. So that is going to be the case. You see, it must be nice. This is it. This is going to be a graph of the polynomial. It's one piece because I start, you know, when I start graphing it, I can go up to the end. I don't need to lift my pen, if you like, to get the numbers. You see, these turning points are nice. We call it a turning point. There's no sharp corner. To get these numbers, it's one piece. There is no holes, no gaps. Okay, so it's going to be smooth, nice, smooth, and okay, and continuous, we call it. So this is going to be a graph of a polynomial. So it's going to be a polynomial graph, if you like, or the graph of a polynomial. A polynomial graph, okay, But if they give you something like this one, you see, look at this one. If this is given to you, that suppose you have something like this is it. This is going to be one piece, okay? And then you are going to have another piece here. Okay, this is not going to be a graph of a polynomial. A graph of the polynomial, because we have over here, okay, there is a gap here. Okay, there is a gap, there is a hole. So it's not going to be, okay, so it is not. It is not a polynomial or graph of the polynomial over here. Okay, so it must be one piece. Okay, just stop here. So you cannot have it. Okay, or you cannot have any sharp corner. You see, I got this one, so I cannot have something like this. Okay, so it must be, this turning point must be smooth, if you like, to get these numbers. Okay, so it is not a polynomial graph, if you like. So it must be nice one, like this one. Okay, nice. So I'll just give you another one because I wanted to ask some question. Look at this one. Look at this graph that I'm going to give you. Okay, this is going to be the graph. Okay, this is going to be the graph. If you want to sketch this graph, what do you need? What is the the thing that you need? You know that you can graph any equation, but just collecting some, okay, by collecting some points. So if you want to graph this one, what do you need? Any suggestion to enable you to graph it?
Probably the intercepts.
Very good. Yes, intercepts. So what do you have? You see, we get 1, 2, 3, 4. These are going to be x-intercepts, okay? These are going to be x-intercepts, and there is a y-intercepts. Y-intercepts is easy to find. You know that because you just let x equal to 0, you get the y-intercepts. But the x-intercepts are interesting. You see the x-intercepts? The x-intercepts are going to be what? It's going to be intersection of the graph and the x-axis. That would help us. Okay, so basically you have to find the intercepts. Okay, intercepts. You let the x equal to 0, you get the y. Okay, then you let y equal to 0, we get the x. So the interesting one are going to be x-intercepts. Okay, x-intercepts. So we have to investigate this because these are going to be more important for us. Okay, when you look at these x-intercepts, can you see any difference between these x-intercepts when you want to graph the function? You know that when you have this point, you know that you have to go through these points. But one of them are different. One of them is different from the other. Which one is it? When we graph it. Any idea? Ding, 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 ding. What's the difference between this one and the others when you want to graph it? This one and this one over here. Any idea? Can you see any difference? Okay, let me tell you. You see, domain of the polynomials are going to be what? Negative infinity to positive infinity. So you can have any numbers. The range is going to be almost, it's going to be, this is going to be the range. It's go up and down. Negative infinity to positive infinity. Okay, there may be some restriction. But the range is the y go up and down. The domain x goes to the right, to the left. Okay, that's going to be one. Now look at this point over here. When we get to this intercept, the graph of the function crosses the x-axis. Cross, because the bottom one is negative. Okay, the bottom one, y is negative. But when you go on the top, y is positive. So for this point, before and after this point, the sign of the y are going to be different, the signs. It's going to be the same for this one because this crosses top and the bottom at the top. But this point over here, you see, for this point, you touches the x-axis. You touch, okay, you touch x-axis and you bounce back. So you are not going to cross this, okay, but over here you cross. So when you want to graph it, okay, this intercepts, it's easy, you know, you let y equal to the 0, you may use factoring to find the x values. But it's important for you to find out, are you going to touch the x-axis at this point or are going to cross? Because if you know it, you know that over here you are not going to go down. You must go up. Okay, so you have to identify when we get these x-intercepts, you have to find out which one will give you the crosses or the touches. It's going to be easy to identify. We look at the sign of the y. Okay, so this is one that we have to describe these intercepts better to be able to get a good understanding. Okay, this is one thing to do. So we have to investigate intercepts. We investigate it. We let f of x equal to 0, and there is a case that quickly we can identify where are going to crosses, where are going to touches. Okay, this is one thing that we have to consider. What next? You see, the next one is a starting point and ending point. You know that the domain of the function is negative infinity up to the negative to positive infinity. So the value of this function, polynomial function, there are two extremes, we call it, that you have to decide. When x goes to positive infinity means x increases without bound. So anything you think about it, there is something above it. When x goes to negative infinity means it's decreasing without bound. Decreasing without bound and increasing without bound. So you have to determine what would happen to the behavior of the function. You see over here, you start from this third quadrant. In the third quadrant, x is negative, y is negative. So x goes to negative infinity, y goes to negative infinity. So you must know this one. Otherwise, how do you know that? How do you know that you are going to coming from the top? Okay, you may come from the top and crosses these points. So you have to determine the behavior of the function. You see the behavior of the function at these endpoints, the extreme ones. And that's very crucial. It's very crucial, not only for this course, it's going to be very crucial when you study calculus. It would be so helpful. So the behavior of the function at these endpoints, we are going to call it end behavior. Okay, and that is something that's quite interesting, and we use it in calculus. Okay, so the end behavior means what would happen to the x, what would happen to the y when x goes to positive infinity or x goes to negative infinity. Okay, so if you identify these two, then you'll be done. Okay, so you have to check what is going to be the end behavior of the function. We do it quickly, it's easy to identify these infinities if you like, and then you have to, okay, then you have to determine what would happen to these intercepts. If we do both things, we are going to come back and do it. These turning points are not going to be important, we can do it. There's something extra that you do in calculus is how far you go up or how far you go down. We call it the maximum and the minimum. But in this course, you just give us an idea of the graph. We sketch the graph. Okay, so I'm going to work on these two. I'm going to work on the end behavior of this type of graphs, these infinities, okay, and the x-intercepts. And when we collect in this information, we come back and we graph it. Okay, any question? So we know that's going to be our road planning flag. So we identify what we need. Now we are going to do it. Okay, so first thing to do is going to be that end behavior of the polynomial. Okay, so what's going to be end behavior? Okay, that's it. What is end behavior? Behavior of a polynomial, polynomial function. Okay, the end behavior of the polynomial function, and that's it. If okay, if y is equal to the f of x is a polynomial function. Okay, is a polynomial, is going to be a polynomial function. Okay, then the behavior, if you like, and then the behavior of f of x or y, f of x whenever x increases or decreases without bound, so this means okay, when x goes to positive infinity or x goes to negative infinity. That's the notation I'm going to use. Increases without bound is going to be called, okay, this behavior is called the end behavior. Okay, end behavior of the function f, if you like, or the polynomial function f. So this is just the behavior of the polynomial function when x increases without bound or decreases without bound. Now, in order to be able to do it, so we need one special case. You see, that is going to be a special case, or cases. So we look at the power function. You see, that's going to be one, power functions. Okay, this is going to be the case. You see the first part. The first part is going to be suppose. Okay, suppose is y is a power function. Y is equal to, let's say, something like x to the n. X to the n where n is even. Okay, so this means y equal to the x squared, y equal to the x to the 4th, x to the 6th. This is what we are going to be interested in this case. Okay, then this is what would happen. You see, when x goes to negative infinity, if you like, means x decreases without bound. Okay, if this is going to be the case, then look at this, y equal to the x to the n. So you see the number is infinity, is increasing. When it's increasing, if you square it, that would be worse. To the 3rd, to the 4th, to the 6th, okay? That getting bigger and bigger and bigger. So the question is going to be, is it going to be increasing without bound to the positive infinity or decreasing? It's a negative, but n is an even number. So any negative numbers to the even number would be positive. So in this case, when x goes to negative infinity, in this case, y goes to, okay, y goes to positive infinity. Okay, you can cheat. Don't substitute. It doesn't make sense. Just the sign. Okay, the number is big, so the result is going to be big. But what is that? Is it positive or negative? Negative to the even number, okay, x squared to the 4th, to this, okay, to the 6th, that make it positive. Okay, and if x goes, you see, this is it, when x goes to positive infinity, then y goes to positive infinity again. Okay, so what does it mean when you want to graph the function? You see, look at this one. This is a negative infinity, this is positive infinity. This is a positive infinity, this is a negative infinity. So when x goes to negative infinity, means you're moving from here. So the value of the function is positive. The positive means it's go up. So in this case, we say it's go up. When you want to graph it, you know that you have to come from this direction. Okay? When x goes to positive infinity, y would be positive. You see, positive, positive. So this means at the end, again, the function goes up. Okay, so it's up, up, if you like, in this case. And that would be useful for us in order, in order to find that. The example is if you get y equal to the x squared. You see y equal to the x squared, you know that this is a quadratic function. We talk about it. So if you want to graph it, you see this is going to be the graph of a function. You see, up, up in this case. And this is a negative infinity, and that's a positive infinity. And this is a positive, and this is going to be negative. Okay, so all the even power, x squared to the 4 to the 6 to the 10 is like this one, is up, up. Okay, so that's one case for the, because for the polynomials, we are going to end up be checking only these powers. So that's why we want it. Okay, any question? So this is when n is even. So what would happen if n is odd? Okay, so what would happen if this n is odd? So this is it, suppose. Okay, suppose y is equal to the x to the n, but n is odd number, where n is odd. N is odd means n cubed to the 5th to the 7th. Okay, so what would happen to the n behavior? If this is going to be the case, then when x goes to negative infinity, what would happen to the y? Then y goes to, you see this is negative. You raise it to the odd power. You raise it to the 3rd, to the 5th, to the 7th. Negative to the odd power would be negative. So in that case, y goes to negative infinity. Okay, so this means if you start from the left, you are going to be in 3rd quadrant, if you like. And what would happen if x goes to positive infinity? Okay, positive to any power would be positive. So that gives you this case this time. So what does it mean? Look at this one. These are the ones that eventually used to graph it. That's the starting point and the end. You see this is negative infinity, and this is a positive infinity. And this is positive, and this is negative. So what you have? X negative, Y negative. X negative, Y negative. So this means when X decreases without bound, the value of the function is going down. So this goes down. Okay? So when X goes to positive infinity, Y would be positive too. Okay? So this is positive, positive. So this means when X goes increasing without bound, so the value of the function would be up. So we say that the function would fall down, down, and then up, down, up, and that would be interesting. That would help us to be able to graph it. Again, the typical example is y equal to the x cubed. Remember, we checked this one before in the library, if you like. So what was the graph of this function? Look at the graph. This is the graph. You see? Down, up, down, up. So that will take care of y cubed, y to the 5th, y to the 7th, y to the 11th, whatever you have. It looks like this one. Okay? You start from negative infinity, you're going down. You end up with the positive infinity, you're going up. Okay, so that will give us an idea of the type of the graph that you are going to have. This would be very helpful when you want to eventually graph polynomials. Okay, any question? Now, why I focus on this one? Because if a polynomial is given to you, remember the polynomial starts with the x to the n minus 1, etc. When x goes to infinity, remember polynomial is a combination of terms. It's a combination of these powers. When these powers are all infinity, so what are you going to have at the end? You're going to have infinity. So what we do if a polynomial is given to us, we shrink it. We shrink it to its leading term, the first one. X to the fifth, x to the seventh, then we check the end behaviors. Great theorem for calculus. Okay, I use this one to give some shortcut when I teach that course. Okay, so if you give me a polynomial, whatever it is, I focus on the leading term. Okay, if you give me 5x cubed minus 3x squared plus 2x minus 1, I don't care about the other terms. I just focus on the leading term. Then I check the end behaviors. Great theorem. Use it in computer science. Okay, they don't like the limits, those type of ideas, but they use this type of ideas here. Okay, so I put them together. We give you the theorem that will take care of the end behavior of the polynomial, and then we are done. Such a useful one if you want to use it in calculus. Okay, so give you theorem. You need this theorem. What is this theorem? This theorem will tell you that the end behavior of a polynomial function is similar to the end behavior of its leading term, the first term. Okay, so there you are. If f, let's say if okay, if f is going to be a polynomial function, okay, we already define it, write it down for you. Okay, then the end behavior, the end behavior of the function of f of x, if you like, is similar to the end behavior of its leading term. Okay, leading term. Okay, you know that the leading term is the terms is going to be the term. Okay, this is going to be the term containing the term containing highest power of the x. Okay, the largest power or the highest power of the variable, let's say x, variable x, that's it. So we shrink it, if you like, just focusing on the leading term, and that gives us a nice theorem. In calculus we define this, we write it down in the form of the so-called limit, but we don't need it, and that gives us the idea. And the leading term is just the power function that I give you. You may have a power, even power of the x, or you may have the odd power of the x, and then you'll be able to do it, and then you're done. Okay, let's give an example to identify what we are talking about. Okay, this is example. We wanted to check, okay, determine the end behavior, of each function, Those function, of course, going to be polynomial function. First one, that's it. F of x equal to the negative 5 x cubed plus 2x squared minus 3x plus 10. You see, we want to know what would happen when x goes to negative infinity or x goes to positive infinity. Okay, so how are we going to do it? Shrink it first. Solution, shrink this function is leading term. You see, this is the leading term of your function. Okay, so you bring the leading term. Okay, we shrink it if you like. F of x, you shrink it into what? Shrink it into negative 5x cubed. Now check the infinity here and tell us what would happen to the f of x. Okay, so start moving. If you see it's odd power, if x goes to negative infinity, then f of x or y goes to, check which one is it. Is it positive infinity or negative infinity? Any suggestion?
Negative.
Let's see why you are wrong. Okay, why negative? You see, negative to the third would be negative, but there is a negative 5 here. So negative would be positive in this case. Okay, so that's why I put the negative 5 here. Okay, that's going to be done because this coefficient would be important. So we check the sign here. You see, negative to the third would be negative, but there is a negative sign outside. So that became to the positive infinity. Any question? Okay, it's like, don't write it down. You can cheat if you like, but don't write it down because if I see it, I'm going to take some points out. Okay, some people, they write it in this form, which is not true. They substitute. They say it's a negative 5 times negative infinity to the third. Okay, then they say it's a negative 5. So negative infinity to the third would be negative. Then negative would be positive. You see, 5 times infinity is just infinity. So they say it's a positive infinity. Okay, but don't write it down. If I see that, I question you. I say, oh, it's another number. Okay, so basically, this is what would happen. So when x decreases without bound, getting smaller and smaller and smaller, what will happen to your function? You see, this is just a combination of powers of x. Just the first one will determine the result. You don't need the others. Okay? So just check the sign. Make sure that if there is a number here, don't miss it. Don't miss that number. X goes to negative infinity, negative to the third would be negative, but negative, positive. Okay, that's first case. Any question? How about the other one? If x goes to positive infinity, what would happen to the function now? Which one is it? Positive infinity or negative infinity?
Negative infinity.
It is negative infinity. Okay, because positive to the third is positive, but there's a negative here. Okay, and that's it. We usually give us, a graph representation if you like to just say, so this is a positive and the negative. You see, this is the starting point of the graph. Negative, positive. Negative, you start here, positive, up. So that the beginning, the graph is coming from here, it's going up. What would happen at the end? Positive, negative, positive, negative. So at the end, it's going down. So when you graph your graph, you see you start from here. You may do something, lots of things, but you end up here. Okay, so that's the end behavior of the function. Very nice, very useful. Okay, any question? That's case one. There are kind of 4 possibilities of this. Just try another one.
How
And
would you
that's your,
know?
yes,
How would you know if x is approaching negative infinity or positive infinity?
you have to do it yourself. Because you know that what's the domain of the polynomial.
You're just doing both. You're
Yeah,
doing both.
that's it. Yeah, that's why we call it end behaviors.
Okay,
Okay,
cool.
that's one. Okay, that's one. So checking another one. Suppose you begin f of x. Okay, f of x equal to, how about x to the fourth? Okay, minus 5x plus 10. You see it's polynomial again. You shrink it. So the solution is going to be, we shrink it. into x to the fourth, the leading term. Okay, now check the infinities. Check the infinities starting from the left. So if x goes to negative infinity, then, okay, your f of x, you see that's easy because negative to the fourth would be positive, and the coefficient is positive here. There is nothing, no negative sign. Okay, so that would be positive infinity. And if you do it the other way around, if x goes to positive infinity, then f of x goes to positive to the fourth would be positive. So it's up, we call it. You see, f of x positive, positive. So this would happen when we graph it. When we graph it, it's a negative infinity, and it's a positive and positive, negative. So this is it. X negative, y positive, negative, positive. So you are going to be here to start, up. You see the graph, raises to the left, up to the left. So positive, 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 up, up. So when you graph your function, you start from here. You may do something, but you end up over there. Okay, so it's going to be up, up. There are four possibilities. You see, up, down, up, down, up, up, down, down. It depends, of these coefficients that are going to give you. Okay, any question? Now, these are a straightforward one for the leading terms. You see this idea of the shrinking, we use even in computer science. It's very old-fashioned things in mathematics. You can search on internet. There is something we call it big O notation. You see, big O. They call it big O notation. It's very old, classic result. Big O notation is something similar to this one. They write f of x is going to be, you see, these type of numbers that we have over here. When we shrink it, they say f of x is, the behavior is big O of the x cube. When they say there's a big O of the x cube, means when x goes to infinity, the behavior of this function are going to be the same. Okay, they call it big O notation. And then, it's like algebra, it's a machine. Then you have two functions, you have f and the g. What would happen to the sum of the f of x plus g of x? The product, the quotient. Okay, it was given by a German mathematician. You just check big O notation, then you will see something interesting. In computer science, sometimes if they want to run a program, and you see, these are the operations that they need. If they want to charge you or to find out how long does it take, they say, oh, this is f of x is a big O of the x to the fourth. Means if you shrink it, you get x to the fourth. So they charge you as x to the fourth. Instead of the machine, the number of the operation that the machine got to do is going to be like x to the fourth. And they have a list of special functions. So quickly they find out what is going to be now the case. So it's very classic result, really. It's not, it's very nice. In calculus, this is big O. The other mathematician created something else. They call it a small O, which is something different, similar. See, a small O of the g of x. These are all estimation at the beginning of the calculus or just the type of application in science. They just estimate everything, okay? But later on, we have a special machine for it. We call it a limit in calculus. So it's quite interesting, concept really. It's not just, we just don't do it for fun to get this graph. There are many, many, many applications in future. Okay, so any question? So that's going to be the one. Now, the one that you are going to see is not in this format. Okay, we are going to give you two problems only. This is going to be the one that you are going to see. Okay, let's see if you can guess how we're going to do this one. You see, eventually you are going to graph this function for me. So look at this one. I give you this function. I can make it as complicated as you like. F of x is equal to Suppose you have something like, let's say, negative 1/2 x squared, okay, x squared times x minus 1 to the fifth, okay, x minus 1 to the fifth times x plus 1, okay. So something like x plus 1, how about, okay, how about to the 8? You see, this is the function that eventually you are going to graph for us. It's polynomial, but they didn't multiply together, okay? Because you need that factoring part, so we don't want you to feel uncomfortable to factoring. So that's why we give you this type of problems. Let's say we're going to find out the end behavior of the graph of this function. You know that you need the leading term. So you have to guess what is going to be the term that contains the highest power of the x, okay? That's your extra job here. Okay, so let's see if we can do it. Solution. You see, we are going to distribute it if you like. But we don't need anything, everything if you like. We just need the leading terms if you like. Let me read, I have to rewrite it to explain it here. Okay, you see when we multiply it, how we're going to get the term containing highest power of the x. You see, you are going to get it if you multiply the highest power of each factor. You see the highest power that you get over here is just a negative 1 over x squared. You see that's going to be the one. Over here, the highest power that you get is x to the fifth. X to the fifth is going to be the higher power that we get here. Okay, the higher power that we get over here is going to be x to the 8. So the leading term, when you multiply it, is something like negative 1/2 x squared times x to the fifth times x to the 8, and something else that we don't care. Okay, so this is how we're going to get the highest power of the x. So what is going to be this? You see, if you multiply them together, that give a negative half. Okay, negative half. What's going to be the power now? X to the 2 plus 5, 7. 7 plus 8 would be, okay, 7 plus 8 would be 15. And something else. Okay, so you are interested in just the term containing the highest power of the x, nothing else. So pick any highest power of the x, you multiply them together. So the shrinking function is going to be what? So f of x would be shrinking to leading term, negative half, okay, x to the 50. Any question? So this is the way you are going to apply it when we get to the actual graphing this polynomial. Now we check the infinity, okay? Check the infinity. What are we going to have? If x goes to negative infinity. If x goes to negative infinity, is what's going to be happen to the function? Then f of x goes to, you see again, look, negative to the 15. 15 is an odd number. So negative to the 15 would be negative, but there is a negative outside. So make it into a positive infinity. Any question? Power first, power first. It's a negative to the 15 would be positive. Okay, but there's a negative outside, make it negative. Sorry, this is going to be negative, 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 make it positive. Okay, the other way around. What would happen if x goes to positive infinity? Okay, if x goes to positive infinity, then what are we going to have over here? Then f of x goes to, okay, positive to the 15 would be positive, but there's a negative sign here. Okay, so that make it into what? Make it into the negative infinity. Okay, x goes to negative infinity, f of x would be positive because this negative would be negative, and over here, so this is going to be the behavior of your function. So that it would be quite helpful because this is it. Now you get your negative infinity and the positive infinity, and that's a positive negative. Okay, and now you know what happened. negative, positive, negative, positive. So at the beginning is up here. Where are going to end up? Positive, negative, positive, negative. Positive means then the function goes down. It's going to be going down. Okay, again, in the meantime, you can go up and down, but eventually this is going to be the situation that you're going to know you're going to have. Okay, so the end behavior is going to be the behavior of the leading term. So we have to shrink it to get that leading term that will be able, to keep up and get these numbers. Okay, any question? So that is the first step. The first step is, okay, I can give you one more of this. In your book, the one that we have are very, but we have this type, You have this nice type in the assignment that we have and in your next test. But the quick one is going to be, you see, this is one of the problem in your book, is a 3x to the fourth. Okay, 3x to the fourth, and this is going to be x minus 1. Okay, x minus 1 to the 6. I want something with the even power so that you can see it. You see, this is easy to shrink. Okay, so the solution is going to be just getting the leading term. You see, this is f of x, and it's given to us that 3x to the fourth times x minus 1 to the 6. Get the leading term, x with the highest exponent. The first one would be just 3x to the fourth. Okay, and the second one is just x to the 6. It's going to be x to the 6. And of course, there are some other terms that we don't care because we are interested in the leading terms. Okay, so this is going to be what? F of x is going to be equal to the 3x to the at the power. 4 and 6 would be 10. 10? Yes, question?
If there was a number in front of that x minus 1, like let's say it was like 5, would you distribute that and then that would be the highest number?
Yeah, if you distribute it, you see if it's 5, it's going to be x fifth.
Yeah.
The highest. But we just need that power. Okay, so you don't need any other terms. Okay, now you know that the indicator function, or the one that you shrink, is going to be 3x to the 10. Okay, so you're going to check the infinity on this one. Okay, which is going to be easy. That's it. If we go from the left, x goes to negative infinity, then f of x goes to, this is it, negative to the 10 would be positive, and the 3 is positive, so that gives you positive. Okay, and the other way around, if x goes to positive infinity, then f of x goes to, is going to be positive infinity, so it's up in this case. Okay, so this is a situation I'm going to have. It's a negative positive. It's nice to get this, but we are not going to do it separately, but it's nice to know it, okay, for the actual one that we have. So negative positive is here, so it's up, and positive is here, is going to be up. You get that graph of the function. Okay, that's the first part, would be enough. This is end behavior. We need to check intercepts. We do it, on Monday. The other one is also easy, but we have to give you a couple of definitions to be able to do it, because we need to find out. So this is the starting point and the end point. Now the x-intercept. You see, look at this one. If you let it equal to 0, you have two solutions. That give you x equal to 0, that give you x equal to 1. Okay, 0 and 1. Now, how we're going to find out whether the graph touches or crosses? We look at this power. You see, if this power is even, Because the zero, the graph would goes to the right and the left of the zero. Means a positive and negative number. If this power is even, the result is always positive. So this means the graph touches the x-axis. Because you see, if you go up and down, you get positive or negative. If it's only positive, you stay on the top. Okay? But if the power is odd, you see, if the power is going to be odd, so if the inside is negative, that give you negative. If the inside is positive, that give you positive. So there is a possibility of positive, negative. So that's why you are going to cross the x-axis, going up or down. Okay, we talk about it and we graph it on on Monday. Nice section, as you can see, it's quite helpful for a future application that we're going to have. And you have a couple of them on your next quiz. Okay, that's it. Any question? So if you haven't sent me your assignment, just do it so that you can get your points. Then I try to grade your your quiz quickly because we need it for the other our next test. And we continue. We have a polynomials function. Then we have something related to the factoring from the past. So a couple of very nice sections really that you are going to like it to get these numbers. Okay. So the assignment, this is it, I think tonight or tomorrow. Where do we turn the assignment? You email me. Email for the assignment, homework, email. We don't,
Professor, is it okay
yes.
if we send it to you through Canvas?
Yeah. I mean, I got both of them on my cell phone. As soon as you send it, I will see it. Okay. But that, it's Zahid, polymer, it would be fine. Yeah. I have the, I saw yours, Christopher. That's it. So as soon as you email it, the personal email would be better. I see it right away. But otherwise, I check it. Yes.
All right, thank you.
Okay, that's one. So just check it. It's a 10 points. Don't miss it. And if you send it, just wait until let's say Friday or Saturday. If you don't see your new 10 points, email me. Okay, but I've already checked a number of them. So you already got 10 points for the first set. So if you send the second one, now you should have a total of 20. If you don't see 20 by a couple of days, then email me. Okay, then I'll check it again for you. That's it. Have a good night. Any question? Okay, take care and see you on Monday. Bye-bye.
Thank you.
Okay, bye-bye.